Hello there. So in this tutorial, I'm going to cover the ndfsmtodfsm algorithm. This was covered in the slides, so we will see that we have the same answer. That's why I picked this one. Now, recall that the epsilon closure of a state Q is the state itself union any other state reached from Q on one or more epsilons. So here I have from 0, I could reach 1, and I could reach 4. Now, of course, by definition, I have to include 0, so that's what we have. Now, I cannot go anywhere on epsilon from 1, so that's why there is no more, and that's why the chain got terminated here. Now, for 1, like I said, it's only itself, and 2, and actually 3, and all of them follow from the same. So we got lucky in this example. Next thing we have is this table that I created. Now, usually if you have more inputs other than AB, you have to include a column for every other input symbol. So our sigma here is simply AB, and that's why I have only AB here. Now, we start with the initial state. So, by the way, in the algorithm, these are called active states. I just call them state because it's simpler. So, our initial state for the new machine is going to have the old initial state, which is 0, but we take the epsilon closure of that. We already have it. That's just over here, 0, 1, 4. So this is our initial state. Right? Now, how do we transition on A? What we gotta do is take the union of all transitions on A from these sets, and we include something extra that we'll talk about. So on 0, where can we go? From 0 on A, I can go to 0, so I include that. Now, whenever you see a transition, so on a letter to some other state, you have to take the epsilon closure of that state. So here I have 0 to 0. I have to compute the epsilon closure of this state over here, okay? So the epsilon closure of this is 0, 1, 4. But since this is a set, we don't repeat the same element twice. We're not going to put 0 again. We're just going to have 1, 4. Okay, now what about 1? Where can I go on A? Well, I can see I can go to 2, so I'm going to have to include 2. So let's do this one over here. So 0 to 2. Now I have to include the epsilon closure of 2, but since this is a set, we already have 2, we don't repeat that. Now from 4, we go nowhere on A, which means we don't include anything. That's it, we're done. Now on B, I'm going to do the same thing. From 0 to 0, I have to include the epsilon transition of 0. Okay, next thing I have 1 on B, I can go nowhere, so I don't include anything. Next thing is 4 on B. So 4 on B is over here. I have to include 5 plus the epsilon closure of 5, but there is nothing in the epsilon closure of, well, there is 5, so I don't include 5 again. Okay, so that's good. All right, that concludes this. Now, whenever you finish a row, you have to look for any new states that you added and add them to your state column. So here 0, 1, 4, 2 is new, so I have to include it. Similarly, 0, 1, 4, 5 is new. Okay. Now, yeah, that's good. So these are not really any special states because they are not initial and not final or accepting. An accepting state would be any state that involves the old final state. So we will see examples of that. So if we had a 3 somewhere, then that would be a final state. But here it's 0, 1, 4, 5 and 0, 1, 4, 2. There's no 3 or no 6, so they are not final states. Now, how do we transition on A from this state? Well, look at 0. On A, it goes to itself, union the epsilon closure, so we do that. On 1, we can go to 2, union the epsilon closure, which is just 2. From 2, I can go to 3 on A, union the epsilon closure, which is 3, but that's already there. All right, next on B. Now from 0, I can go to 0, union the epsilon closure of 0. And from 1, I can go I'm here. Yeah, from 1, I can go nowhere on B, so I don't do anything. And from 4, I can go to 5 on B, so I have to include that. And from 5, I can go to 6. Now, I'm ignoring the epsilon closures because the epsilon closure of every set is itself. So if I add 5, so let's say if I have like 4 to 5, I add 5 because I can reach it from 4, but the epsilon, and I have to add the epsilon closure of 5, but that's just 5. And again, we cannot repeat the elements in this set, so that would be meaningless. But you have to be careful if this was a different example. You have to always add the epsilon closure of 5 as well. But in this case, again, it's just 5. And from 5, I add the epsilon closure. Oh, damn, what is this? So 4 to 5, yeah, and that's it. And then 2, well, it does not go anywhere on B, so that's good. Next thing we have 0, 1, 4, 5. Well, on 0, A remains the same, so 0, 1, 4. On 1, I can go to 2. The epsilon closure of 2 is 2, so nothing to add. And then on 4, let's see, from 4 on A, I can go nowhere. On 5, from 5 on A, I can go nowhere, so that's it. Well, what about B? Well, from 0, 0 plus the epsilon closure, so 0, 1, 4. What about 1? I can go nowhere, so nothing. From 4, I can go to 5. Epsilon closure of 5 is still 5, so nothing to add. From 5, I go to 6 on B, so I add 6, plus the epsilon closure of 6, which is 6, so nothing to add. Okay, now any new states? Yep, we have 0, 1, 4, 2, 3. Okay, now notice this includes 3. 3 was my former accepting state, which means this is going to be an accepting state. Okay, now from 0, 1, 4, 2, 3 on A, how do we do this? Well, we look at 0 again. On A, it goes to 0 plus the epsilon closure. On 1, I go to 2. On 2, I can go to 3. And I skip 4 because you cannot go anywhere from 4 on A. Okay, so that's 0, 1, 4, 2, 3. And I believe that's it. Because from 3 on A goes nowhere as well. Okay, next thing we do is B. We start from 0 again. 0 goes to itself, plus the epsilon closure of 0, so 0, 1, 4. Now, where does 1 go on B? Nowhere. Where does 4 go on B? 5. 5, epsilon closure is still 5. Where does 2, where does 2 go on B? Goes nowhere. Where does 3 go on B? Nowhere. So that's it. Okay, now any new state we added here. I have this one check, 0, 1, 4, 2, I have it here. So look at the order, it's different sometimes, but because it's a set, so it doesn't matter how the order is written. 0, 1, 4, 5, 6, we don't have that, so we write this. Of course, if you don't want to confuse yourself, you can put them all in numerical order so that you can easily identify which one's missing, but yeah. So 6 is a final state, as you can see here. So what we're going to do is going to call this one as well an accepting state. Okay, now where do we transition on A from this state? So 0 goes to itself plus the epsilon closure, 1 goes to 2 plus the epsilon closure, and 4 goes nowhere, 5 goes nowhere on A, and 6 goes nowhere on A, so we're done. Okay, what about B? 0 goes to the epsilon closure itself, so that's 0, 1, 4. 4 goes to 5. 5 goes to 6. 6 goes nowhere. We're done here. Okay, and that's what we have. So, in fact, we don't have any more new states, so we are done with the table. Next thing we do is make our diagram. So, oops. So let me just draw the. Okay, so that's 0, 1, 4. And on A, I can go to 0, 1, 4, 2. Now I'm going to use the numeric order just because that's what the prof does. 1, 0, 1, 2, 4. Okay. Oh, that looks a bit ugly. I'm going to redraw that. 0, 1, 2, 4. Okay. Then on B, we go to 0, 1, 4, 5. Okay. Next, we've got on okay, from 0, 1, 2, 4, I can go to 0, 1, 4, 2, 3, which I'm going to use alphabetic order again, or numeric order. 0, 1, 2, 3, 4. Now, this is the final state because it includes the 3. Okay. Now, from 0, 1, 2, 4 on B, I go to 0, 1, 4, 5, which is the one below this. Okay. So we get that on B. Okay. And this completes this second row. The third row has 0, 1, 4, 5. On A, it goes to 0, 1, 4, 2. So I include that. And on B, it goes to 0, 1, 4, 5, 6. I have to create a new state here. 0, 1, 4, 5, 6. Okay. And that finishes the third row. Fourth row, we have 0, 1, 4, 2, 3, which is this one. On A, goes to itself. On B, goes to 0, 1, 4, 5. Okay, that's on B. All right. Next is 0, 1, 4, 5, 6. On A, goes to 0, 1, 4, 2. So the one over here. And on B, it goes to itself. And this concludes our example. This is the answer from the slide, so I'm just gonna check to see if it's the same. Let me see if I can just move it up so we can compare. There we go. So we have 0, 1, 4, 0, 1, 4, 0, 1, 2, 4, 0, 1, 4, 5. Same transitions. Perfect. There we go. So I hope that this helps, and if you have any questions, leave them down in the comments.